Welcome back to Record Rift, where we uncover the hidden secrets of history. Today, we're diving into a mystery that has puzzled scientists for years. Roman concrete, also known as opus cementitium, was a revolutionary building material that allowed the Romans to construct enduring structures such as aqueducts, temples, and the famous Roman Pantheon. Unlike modern concrete, which uses Portland cement, Roman concrete was made by combining volcanic ash, pozzolana, lime, calcium oxide, and seawater to form a mortar, which was then mixed with aggregates like pumice, stones, and gravel. The key to Roman concrete's durability was its unique composition, particularly the volcanic ash, which helped it resist cracking and degradation over time. The use of seawater in the mix led to a chemical reaction that made the concrete more resilient, even underwater. This quality made it ideal for constructing harbors and underwater structures that have lasted for millennia. One of the most notable structures built using Roman concrete is the Pantheon in Rome, with its massive dome, which remains the largest unreinforced concrete dome in the world today. Roman concrete was not only strong but also versatile, allowing for the creation of complex forms, including arches and vaults, that were critical to Roman architectural achievements. Roman concrete fell out of use after the decline of the Roman Empire, and its precise methods were largely lost until modern times, when engineers began studying ancient Roman construction to understand its resilience. This ancient material remains a subject of fascination and is seen as a remarkable example of Roman engineering ingenuity. Roman concrete was composed of several key ingredients that, when mixed in specific proportions, produced a highly durable material. The primary components were pozzolana, volcanic ash. The most distinctive ingredient in Roman concrete was pozzolana, a type of volcanic ash found in regions like the Bay of Naples. It was rich in silica and alumina, and when mixed with water and lime, it formed a chemical bond that gave Roman concrete its remarkable strength and water-resistant properties. Lime, calcium oxide. Lime, produced by heating limestone, was used to create the binding agent in the concrete. When lime was mixed with water, it created a paste that hardened over time. This paste, when combined with pozzolana, formed a hydraulic cement capable of setting underwater, which was a key factor in the longevity of Roman concrete. Seawater. Unlike modern concrete, which uses fresh water, Roman builders often use seawater in the mix, especially for structures like harbors and underwater constructions. The seawater reacted with the pozzolana and lime, forming compounds that enhanced the concrete's ability to resist cracking and environmental degradation, even in marine environments. Aggregates, pumice, stones, and gravel. Various aggregates were mixed into the mortar to provide bulk and strength. Pumice, a lightweight volcanic rock, was often used due to its porous nature, which helped reduce the overall weight of the concrete. Other aggregates, such as stones and gravel, were added for structural integrity, ensuring the concrete could withstand heavy loads and stresses. Water. Water was essential for activating the chemical reactions between the lime and pozzolana. The correct amount of water was crucial for ensuring the right consistency and allowing the concrete to cure properly. The combination of these materials created a durable, versatile substance that could be poured into molds to form shapes like arches, vaults, and domes, enabling the Romans to build sophisticated architectural structures that could last for centuries. The chemical interactions between these materials also allowed Roman concrete to harden and gain strength over time, making it even more robust as it aged. Modern concrete has a different composition compared to Roman concrete, as it uses more advanced materials and additives. The primary components of modern concrete include cement, Portland cement. The binder in modern concrete is Portland cement, a mixture of limestone, clay, and other materials that are heated together in a kiln. When combined with water, cement forms a paste that hardens and binds the aggregates together. Portland cement is much more refined than the lime used in Roman concrete and is responsible for giving modern concrete its strong structural properties. Water. Water is essential in modern concrete as it reacts with cement to form calcium silicate hydrate, CSH, the gel-like material that gives concrete its strength. The water-to-cement ratio is crucial to ensure that the concrete mixture achieves optimal strength and durability. Too much water can weaken the concrete, while too little can prevent it from properly curing. Aggregates, fine and coarse. Fine aggregates. Sand is used as the fine aggregate in modern concrete, providing a smooth texture and filling the gaps between larger aggregates. It helps reduce the overall volume of cement needed while still maintaining the desired consistency. Coarse aggregates, gravel or crushed stone. Larger particles like gravel or crushed stone provide structural strength to concrete and reduce shrinkage as it cures. The size and type of coarse aggregates depend on the specific requirements of the project, such as load-bearing capacity and durability. Admixtures optional. Modern concrete often includes chemical additives, known as admixtures, which modify its properties. These can include plasticizers, water reducers. These reduce the amount of water needed in the mixture, improving workability without compromising strength. Accelerators. These speed up the curing process, especially useful in cold weather. Retarders. These slow down the curing process, providing more time to work with the concrete, especially in hot weather. Air entraining agents. These create microscopic air bubbles within the concrete, which improves its freeze-thaw resistance and makes it more durable in harsh climates. Fibers, e.g., steel or synthetic fibers, may be added to improve the concrete's tensile strength, reduce cracking, and enhance impact resistance. Supplementary cementitious materials, SCMs. In addition to Portland cement, modern concrete often contains supplementary materials like fly ash. A byproduct of coal combustion, fly ash can replace a portion of Portland cement, making the concrete more sustainable and enhancing its long-term durability. Slag cement. A byproduct of steel production, slag can also replace part of the cement and improve the concrete's resistance to chemical attacks. Silica fume. A byproduct of silicon production, silica fume is added to increase concrete's strength, density, and resistance to corrosion. Modern concrete has a much greater variety of materials and additives compared to its Roman counterpart. These advancements allow for a wide range of performance characteristics, such as increased strength, durability, workability, and sustainability, depending on the needs of the project. However, unlike Roman concrete, modern concrete often faces issues like cracking and degradation due to its more chemically complex composition and reliance on Portland cement, which is energy-intensive to produce. Roman concrete was notably stronger and more durable than modern concrete for several key reasons, many of which are rooted in its unique composition and the chemical properties of the materials used. Here's a breakdown of why Roman concrete has stood the test of time. 1. Volcanic ash, pozzolana, and its chemical properties. One of the most important factors behind the strength of Roman concrete is the use of pozzolana, a type of volcanic ash. When combined with lime and water, pozzolana triggered a chemical reaction that produced calcium aluminum silicate hydrate compounds, CSH, which are very stable and resistant to cracking. This reaction created a type of hydraulic cement that could set and harden underwater, making it ideal for building harbors, bridges, and other marine structures. The pozzolana not only gave Roman concrete exceptional durability but also helped it to resist environmental factors like erosion, seawater, and chemical decay, which modern concrete is more susceptible to. 2. Reaction with seawater. When Roman concrete was mixed with seawater, it created additional chemical reactions that enhanced its strength. The seawater reacted with the pozzolana to form a rare mineral called aluminum tobermarite, which made the concrete more resilient to cracking over time, especially in wet or marine environments. In contrast, modern concrete, when exposed to seawater, tends to suffer from chloride-induced corrosion, weakening the material over time. Roman concrete, on the other hand, became stronger with age due to this ongoing chemical process. 3. Slow hydration and long-term strength gain. Roman concrete's strength didn't just come from initial setting, but from the way it continued to gain strength over time. The chemical reactions in Roman concrete were slower than in modern Portland cement, which means that the material kept hardening and strengthening for centuries. Modern concrete tends to gain strength quickly after curing but can lose durability over time due to cracks, environmental exposure, and chemical degradation. 4. Lack of cracking. The combination of volcanic ash and lime, along with the slow-setting nature of Roman concrete, resulted in a material that was much less prone to cracking. The material's inherent ability to resist cracking is one reason why Roman structures, like the Pantheon, remain intact after more than 2,000 years. Modern concrete, by contrast, tends to crack over time due to its faster setting nature, exposure to moisture, and the limitations of Portland cement, which can shrink and crack as it dries. 5. Microscopically dense structure. The chemical reactions in Roman concrete formed a dense microstructure, which helped it resist both physical wear and chemical degradation. The bond between the aggregates, like pumice and stones, and the binder, lime and pozzolana, was exceptionally strong, contributing to the material's longevity. Modern concrete, although strong, can sometimes have a more porous structure, which makes it more vulnerable to cracking, water penetration, and chemical attacks, especially in harsh environments. 6. Use of natural, locally available materials. The Romans didn't rely on the highly processed materials we use today. They utilized locally sourced volcanic ash and aggregates, which were both abundant and incredibly well-suited to their needs. The natural composition of these materials contributed to the concrete's robustness and long-lasting qualities. Modern concrete, in contrast, relies on more industrial processes and synthetic materials like Portland cement, which requires significant energy to produce and is less resilient in certain environments. 7. Hydraulic cement properties. Roman concrete's hydraulic properties allowed it to be used in underwater constructions, such as piers, breakwaters, and harbors, where modern concrete might degrade or require additional protective coatings. The ability of Roman concrete to set and harden underwater without deteriorating over time contributed to its strength and longevity. 8. Sustainability and low environmental impact. In addition to its strength, Roman concrete's sustainability played a role in its lasting impact. The use of volcanic ash, a naturally abundant and locally sourced material, meant that the environmental cost of producing Roman concrete was minimal compared to the energy-intensive production of modern Portland cement. 9. Evolution and adaptation over time. Roman concrete, especially in marine environments, underwent a natural process of self-healing. As cracks or fractures appeared, the chemical compounds continued to react with the environment, like seawater, filling in the gaps and strengthening the material further. Over centuries, this self-healing process made Roman concrete more durable as it aged. Modern concrete doesn't have this self-healing property to the same extent, although new technologies, such as self-healing concrete, are being explored today. In summary, Roman concrete's superior strength can be attributed to its unique composition, especially the use of volcanic ash and lime, its chemical interaction with seawater, its slow setting process that promotes long-term strength gain, and its resistance to cracking and environmental degradation. These factors combine to make Roman concrete not only stronger than modern concrete in many ways but also much more durable, particularly in marine and challenging environments. Despite the advancements in concrete technology, Roman concrete remains a marvel of ancient engineering, and modern scientists continue to study its properties to improve today's construction materials. The technological and material differences between Roman concrete and modern concrete are substantial and play a crucial role in the performance, durability, and overall characteristics of each material. Here's a deeper look at how they differ in terms of both technology and materials. 1. Materials used. Roman concrete. Pozzolana, volcanic ash. The key ingredient in Roman concrete was pozzolana, a naturally occurring volcanic ash found in regions like the Bay of Naples. This material reacted with lime and water to create a strong, durable binder that improved the concrete's strength and longevity, especially in underwater environments. Lime, calcium oxide. Roman builders used lime as the primary binder, obtained by heating limestone in a kiln. When mixed with water, lime formed a paste that reacted with pozzolana to produce hydraulic cement, which could harden underwater and resist chemical decay. Seawater. Seawater was often used in the mix, particularly for marine structures like piers and breakwaters. The salt water reacted with the pozzolana to form additional minerals, making the concrete even more durable and resistant to cracking over time. Natural aggregates. Roman concrete commonly used aggregates like pumice, gravel, and stones. The use of lightweight aggregates such as pumice helped reduce the overall weight of the concrete, while maintaining strength. Modern concrete. Portland cement. Modern concrete is made primarily with Portland cement, a highly refined product created by heating limestone, clay, and other materials to high temperatures in a kiln. Portland cement, when mixed with water, forms a paste that binds aggregates, sand, gravel, crushed stone, together. Water. Water is required to activate the cement and initiate the hydration process. The water-to-cement ratio is crucial in determining the strength of the concrete. Aggregates, fine and coarse. Modern concrete uses fine aggregates, sand, and coarse aggregates, gravel or crushed stone, to provide strength, reduce shrinkage, and control the weight of the final product. Admixtures. Modern concrete often includes various chemical additives or admixtures, such as plasticizers, accelerators, retarders, air entraining agents, and fibers, to modify the properties of the concrete. These are designed to improve workability, curing times, durability, or resistance to specific environmental conditions. 2. Chemical processes and reactions. Roman concrete. Hydraulic setting reaction. Roman concrete was a hydraulic binder, meaning it could set and harden underwater due to its unique chemical properties. The reaction between lime and pozzolana produced a highly stable and long-lasting cement matrix that continued to gain strength over time. Mineral formation. When exposed to seawater, Roman concrete formed rare minerals like aluminum tobermarite, which added to its long-term strength and resistance to cracking. Self-healing properties. The chemical reactions in Roman concrete were slow and gradual, which meant that over time, the material actually strengthened. If cracks appeared, the minerals in the concrete would continue reacting with the environment, filling gaps and making the concrete more robust. Modern concrete. Hydration of Portland cement. In modern concrete, the hydration of Portland cement, the chemical reaction between water and cement particles, leads to the formation of calcium silicate hydrate, CSH, which gives concrete its strength. This process is fast initially but slows down over time, with the concrete reaching its full strength after a period of curing. Limited self-healing. Modern concrete does not have the same self-healing properties as Roman concrete. While there are new technologies being developed, such as self-healing concrete using bacteria or specialized polymers, traditional Portland cement concrete is more prone to cracking and degradation over time, especially under harsh conditions. Chemical degradation. Modern concrete is susceptible to chemical degradation, particularly in marine environments. Chloride ions from seawater can corrode the steel reinforcement inside concrete, leading to cracks and structural failures. This is one of the reasons modern concrete is more vulnerable and long-term exposure to seawater compared to Roman concrete. 3. Durability and longevity. Roman concrete. Long-term durability. Roman concrete is renowned for its ability to withstand the test of time, with some structures lasting over 2,000 years. This is largely due to its unique chemical composition, including the volcanic ash and its ability to resist cracking and degradation. Additionally, its resistance to seawater corrosion is unparalleled. Resilience in marine environments. Roman concrete structures, such as underwater piers, have survived in harsh marine environments, even when exposed to waves and salt water for millennia. The ongoing chemical reactions in the material made it stronger over time, ensuring its durability. Modern concrete. Lifespan and maintenance. Modern concrete typically lasts for decades but often requires maintenance or repair due to cracking, environmental exposure, and steel reinforcement corrosion. While reinforced concrete is designed to improve structural strength, it is still vulnerable to chemical attacks, like sulfate attack, and physical degradation over time. Vulnerability to cracking. Cracking is a common issue with modern concrete, especially as it ages. While cracks may be small initially, they can grow over time, leading to structural issues if not addressed. The main cause of cracking in modern concrete is the shrinkage that occurs as the material cures, compounded by external stresses and environmental conditions. Technological advancements and construction techniques. Roman concrete. Masonry and formwork. Roman builders used a variety of construction techniques, including wooden molds and scaffolding to form the concrete. They were skilled at creating intricate, long-lasting forms like arches, domes, and vaults. Roman concrete was often poured in layers and allowed to set slowly, which minimized cracking during the curing process. Monolithic structures. Roman builders frequently used concrete in monolithic structures, where large, single pieces of concrete were poured and allowed to set as a unified mass. This helped eliminate weak joints or seams that could lead to cracking. Modern concrete. Reinforced concrete. The major technological advancement in modern concrete is reinforced concrete, where steel rebar or mesh is embedded within the concrete to enhance tensile strength. This allows modern concrete to bear much heavier loads than Roman concrete, which was not reinforced with metal. Precast and pre-stressed concrete. Modern construction techniques also include the use of precast concrete components and pre-stressed concrete, where tension is applied to the concrete before it is poured to increase strength and reduce cracking. These technologies allow for faster construction and more complex designs but also introduce the risk of internal stress and cracking. Advanced formwork systems. Modern construction uses sophisticated formwork systems, which can mold concrete into nearly any shape. These systems allow for greater control over the quality and consistency of the concrete but require more advanced technology and materials. 5. Environmental impact. Roman concrete. Low environmental impact. The production of Roman concrete was relatively low in terms of energy use and environmental impact. The materials, such as volcanic ash, were naturally occurring and abundant, and the process of making lime was less energy-intensive compared to modern cement production. Sustainability. The use of local, natural materials also made Roman concrete more sustainable, with minimal waste or reliance on industrial processes. Modern concrete. High carbon footprint. Modern concrete, particularly Portland cement, has a significant environmental impact. The production of Portland cement is energy-intensive, accounting for a large percentage of global carbon dioxide emissions. This has led to a growing interest in making concrete more sustainable by replacing some of the cement with alternative materials like fly ash, slag, or silica fume. Efforts for sustainability. In recent years, efforts have been made to improve the environmental footprint of concrete. Technologies such as carbon capture and storage (CCS) and the use of alternative binders, e.g., geopolymer concrete, are being researched and implemented to reduce concrete's environmental impact. The technological and material differences between Roman and modern concrete are significant. Roman concrete was made from natural, locally sourced materials that formed a durable, self-healing material over time, ideal for marine environments. Modern concrete, while stronger in some ways due to reinforcement and additives, relies on more energy-intensive processes, is more prone to cracking, and faces greater environmental challenges. The long-lasting performance of Roman concrete offers valuable lessons for modern construction, particularly in terms of material sustainability and durability. Ancient Roman construction techniques were highly advanced for their time and played a pivotal role in the enduring success of Roman architecture and engineering. Romans were known for their ingenuity and use of innovative methods, materials, and tools that allowed them to create structures that still stand today. Below are some of the most significant Roman construction techniques. 1. Use of concrete, opus cementitium. Roman concrete. As discussed earlier, Roman concrete was a revolutionary material that allowed Romans to build large, complex, and durable structures, including aqueducts, roads, bridges, baths, and monumental buildings like the Pantheon. Unlike modern concrete, Roman concrete incorporated volcanic ash, pozzolana, lime, water, and aggregates such as pumice, which made it more durable, especially in marine environments. Opus cementitium. This is the term for Roman concrete, which was often used in conjunction with stone and brick. Roman builders typically poured concrete into wooden molds or formwork to create large walls, vaults, and domes. It allowed them to build faster and more flexibly, enabling the construction of arches, vaults, and other complex forms. 2. Roman arches and vaults. Arches. The use of the arch was one of the most significant innovations of Roman engineering. Arches distribute weight evenly and create strong, stable openings. This allowed Romans to construct large bridges, aqueducts, and doorways with relatively little material. The Roman arch is still a cornerstone of modern architecture. Vaults. Building on the concept of the arch, the Romans developed vaults, which are essentially a series of arches placed together to create a roof or ceiling. There are different types of vaults, including barrel vaults, a series of connected arches, creating a tunnel-like structure. Groin vaults, two intersecting barrel vaults, which allowed for more flexibility in space usage and improved stability. Rib vaults. These featured a framework of ribs that supported the weight of the roof and were later used extensively in Gothic architecture. Domes. The Roman Pantheon is a prime example of the use of a concrete dome, the largest unreinforced concrete dome in the world. Roman domes were made possible through the use of concrete, and they allowed for the construction of massive, open interior spaces without the need for support columns. 3. Opus reticulatum and opus lateritium. Opus reticulatum. This technique involved the use of small, square or diamond-shaped stones arranged in a regular pattern, creating a net-like appearance. It was commonly used for facing walls and provided both strength and a decorative aesthetic. The stones were often made of tuff or volcanic rock, which was lightweight yet durable. Opus lateritium. This technique used bricks instead of stone. Bricks were often made from clay and fired to create uniform blocks. Opus lateritium was particularly useful for building large walls and was often used in conjunction with Roman concrete for greater structural strength. 4. Roman roads and pavement. Road construction. The Romans were renowned for their extensive network of roads, which connected the empire and facilitated trade, communication, and military movement. Roman roads were built using a multi-layer system. Statumen, the first layer, made of large stones, provided a solid foundation. Rudis, a second layer made of smaller crushed stones mixed with lime. Nucleus, a finer layer of sand or gravel. Summa crusta, the final layer of large, flat stones, often with a cambered, sloped surface to facilitate drainage. Durability. Roman roads were designed to be long-lasting, with some surviving to the present day. Their durability was achieved through the careful layering of materials and the incorporation of drainage systems. 5. Aqueducts and water management. Aqueduct construction. The Romans built sophisticated aqueducts to transport water from distant sources to their cities, ensuring a reliable water supply for public baths, fountains, and private households. Roman aqueducts consisted of three main parts. Water source, often a spring or river located far from the city. Channels, stone or concrete channels were dug to carry water, often underground. Bridges/arches. When the terrain was uneven, aqueducts were supported by bridges or arches to maintain a steady gradient. This enabled the water to flow under gravity. Water distribution. Water was distributed through a complex network of pipes, fountains, public baths, and private plumbing systems. Lead pipes, fistulae, were often used for water distribution, though they were later discovered to have led to health issues. 6. Roman construction tools and equipment. Wooden scaffolding. Romans used wooden scaffolding to build tall structures. This scaffolding was critical for constructing large buildings like temples, amphitheaters, and basilicas. The scaffolding would allow workers to reach higher levels and support formwork during the construction process. Cranes and winches. Romans employed cranes to lift heavy building materials, especially when constructing monumental structures. These cranes often used a combination of pulleys and winches to lift stones and other heavy items. Molds and formwork. For concrete structures, the Romans used wooden molds or formwork to shape the material as it cured. The use of formwork allowed for the construction of complex shapes, such as domes and arches, with concrete. 7. The use of prefabricated elements. Precut stones and bricks. The Romans often used prefabricated stone or brick elements for their buildings. These materials were cut to a specific size and shape at quarries and then transported to construction sites for assembly. This helped streamline the construction process and allowed for greater precision and efficiency. Modular construction. Some Roman buildings, such as temples and large public structures, used modular construction methods, where standardized elements could be assembled in different configurations. This reduced the amount of on-site labor and sped up construction time. 8. Architectural design and symmetry. Symmetry and proportions. Roman architects paid close attention to symmetry, proportion, and the relationship between parts in their designs. For example, the use of columns, pediments, and porticos in temple designs was based on strict guidelines of proportion, ensuring that buildings were aesthetically pleasing and structurally sound. Classical orders. Roman architecture incorporated the classical orders of architecture, Doric, Ionic, and Corinthian columns. Romans were known for their refinement of these styles, creating grand public buildings and temples with columns that not only served a structural purpose but also conveyed grandeur and authority. 9. The Roman hypocaust system. Underfloor heating. The hypocaust was an innovative heating system used in Roman baths and villas. It involved a furnace that heated air, which was then channeled under floors raised on pillars, warming the rooms above. This system allowed for efficient heating in large public bathhouses, making them more comfortable during colder months. 10. The use of domes and large interior spaces. Domed structures. Romans were pioneers in the use of domes, which were made possible through the use of Roman concrete. The Pantheon, with its massive unreinforced concrete dome, is a prime example of Roman expertise in creating large, open interior spaces. The use of a coffered ceiling, a series of sunken panels, and the Pantheon also helped reduce the weight of the dome while maintaining its strength. 11. Roman villas and housing. Villa architecture. Roman villas were luxurious rural homes designed with multiple rooms, including dining areas, private baths, and garden spaces. Roman homes often incorporated courtyards, atrium, and peristyles, colonnaded gardens, designed to optimize natural light and ventilation. Insulae, urban apartments. In crowded cities like Rome, many Romans lived in insulae, which were multi-story apartment buildings. These buildings were constructed using brick or concrete and were often built in a modular fashion, with shops on the ground floor and living quarters above. Roman construction techniques were advanced and diverse, allowing the Romans to create a vast array of enduring structures that continue to influence modern architecture. From the innovative use of concrete to the development of arches, vaults, and domes, Roman builders mastered both functional and aesthetic design. Their use of modular construction, water management systems, and heating technologies further demonstrates their sophistication and understanding of engineering. Many of these techniques are still in use today, and Roman structures remain lasting symbols of their engineering prowess. Modern concrete construction has revolutionized the building industry, enabling the creation of skyscrapers, bridges, highways, dams, and many other essential structures. However, despite its widespread use and proven durability, modern concrete construction faces several challenges that impact its performance, environmental sustainability, and long-term viability. These challenges include issues related to material degradation, environmental impact, and construction processes. Below are some of the key challenges facing modern concrete construction. 1. Cracking and shrinkage. Cracking. One of the most common and persistent challenges with modern concrete is cracking. Concrete is prone to cracking due to various factors, including shrinkage. Concrete naturally shrinks as it cures, which can cause cracks if the curing process is not controlled. This is especially true in large pores where the exterior cures faster than the interior, leading to tension and cracking. Thermal stress. Temperature fluctuations during curing or over time can cause the concrete to expand and contract, leading to stress and cracks. Settlement cracks. These occur as concrete settles due to the weight of the structure or shifting of underlying soil or foundation. Impact of cracking. Cracks not only compromise the aesthetic appearance of concrete structures but also weaken their integrity, allowing moisture and harmful chemicals to penetrate. Over time, this can lead to corrosion of steel reinforcement, rebar, and structural failure if not addressed. 2. Reinforcement corrosion. Steel corrosion. Concrete is typically reinforced with steel rebar to provide tensile strength. However, when water and oxygen penetrate cracks in the concrete, they can reach the steel reinforcement, causing it to corrode. This corrosion produces rust, which expands and exerts pressure on the surrounding concrete, leading to further cracking and spalling. Chloride-induced corrosion. One of the biggest culprits of steel corrosion in concrete is the presence of chloride ions, particularly from seawater or de-icing salts. These chlorides can break down the protective passive layer around the steel reinforcement, accelerating the corrosion process. Sulfate attack. Concrete exposed to sulfates, often from the soil or groundwater, can undergo a chemical reaction that leads to the formation of expansive products, causing the concrete to crack and deteriorate. 3. Durability in harsh environments. Marine environments. Concrete used in marine environments, such as piers, docks, and underwater structures, faces significant challenges due to the constant exposure to seawater, which accelerates corrosion and degradation. The high chloride concentration in seawater poses a threat to both the concrete matrix and steel reinforcement. Freeze-thaw cycles. In cold climates, freeze-thaw cycles can cause serious damage to concrete. Water that penetrates the concrete structure expands when it freezes, creating internal pressure and causing the concrete to crack and deteriorate. While errant training agents can help mitigate this issue, freeze-thaw damage remains a concern in exposed environments. Acid rain and chemical attacks. Concrete exposed to acid rain or industrial pollutants, like sulfur dioxide or carbon dioxide, can undergo chemical reactions that degrade the material, causing surface erosion and weakening the structure over time. 4. Environmental impact. High carbon footprint. The production of Portland cement, the primary binding agent in modern concrete, is highly energy-intensive and contributes significantly to global carbon dioxide (CO2) emissions. The process of heating limestone and clay in kilns to produce cement accounts for about 8% of global CO2 emissions, making concrete production one of the largest industrial contributors to climate change. Raw material extraction. The mining of limestone, clay, and other materials used in concrete production can lead to environmental degradation, including habitat destruction, soil erosion, and water pollution. The extraction process also consumes large amounts of energy. Waste generation. Concrete construction and demolition waste, C&D waste, is another major environmental issue. While concrete can be recycled, much of the material ends up in landfills, contributing to environmental pollution. Additionally, large quantities of water are often used during the production and mixing of concrete. 5. Concrete mix design and quality control. Mix design complexity. The design of a concrete mix requires a careful balance of ingredients, cement, water, aggregates, and admixtures. An incorrect mix ratio can result in a concrete that is either too weak or too brittle. Achieving the right balance of workability, strength, and durability is challenging, especially when considering the specific requirements of the project. Quality control. Maintaining consistent quality in the production of concrete is crucial for ensuring the safety and longevity of the structure. Variations in raw materials, mixing, transportation, and curing conditions can lead to significant differences in the quality of the final product. Poor quality control can result in defects, reduced strength, and premature deterioration. 6. Sustainability and alternative materials. Over-reliance on Portland cement. As mentioned, Portland cement has a significant environmental impact, and while efforts have been made to reduce its carbon footprint through alternatives such as blended cements, containing fly ash, slag, or silica fume, these options are still not widely adopted. Innovative materials. Research is underway to find more sustainable alternatives to traditional concrete materials. Geopolymer concrete, which uses industrial byproducts like fly ash or slag as binders instead of Portland cement, has shown promise in reducing carbon emissions. However, widespread adoption of such materials is still limited due to cost, production challenges, and a lack of standardized guidelines. Recycled concrete aggregates (RCA). Using recycled aggregates from demolished concrete structures is a sustainable alternative that can help reduce waste. However, the quality and consistency of RCA can be an issue, as it can sometimes lead to lower strength concrete when not properly processed. 7. Time and labor intensive curing process. Curing time and strength development. Concrete needs to cure for a specific period, typically 28 days, to develop its full strength. During this curing period, the concrete must be kept at the right temperature and moisture level. In hot or dry climates, special curing methods, such as wetting, covering with plastic sheets, or using curing compounds, are required to prevent the concrete from drying too quickly, which can lead to cracking. Delayed construction and weather challenges. Concrete construction is also impacted by weather conditions. Extremely cold or hot weather can affect the curing process and the ability to achieve optimal strength. The need to schedule pours carefully and monitor curing conditions can lead to delays and increased project costs. 8. Workability and forming challenges. Workability. While modern concrete can be engineered to have various properties, achieving the right workability for specific applications can be difficult. Concrete needs to be fluid enough to be poured into molds or forms, yet strong enough to retain its shape and strength. Additives and plasticizers are often used to improve workability, but this can increase the cost of the material. Formwork. Creating the molds or formwork required to shape concrete into the desired form can be time-consuming and costly. Formwork must be precise and robust enough to hold the weight and pressure of the concrete until it sets. Additionally, the formwork needs to be removed once the concrete has cured, which can sometimes be challenging, especially in complex or large-scale projects. 9. Inadequate maintenance and long-term performance. Maintenance requirements. Despite its strength, modern concrete requires ongoing maintenance to ensure its longevity. This includes sealing cracks, addressing corrosion issues, and applying protective coatings to prevent moisture and chemicals from infiltrating the material. Inadequate maintenance can accelerate degradation and reduce the lifespan of the structure. Aging infrastructure. Many concrete structures, especially in older urban environments, are showing signs of wear due to years of exposure to harsh conditions. The challenge is not only in repairing these aging structures but also in ensuring that repairs themselves don't introduce new issues. 10. Limited adaptability for certain applications. Complex geometry. While concrete is highly versatile, it can be difficult and costly to achieve complex shapes and intricate designs, particularly without the use of advanced technologies like 3D printing or custom formwork techniques. Additionally, concrete's brittle nature means it's less suited for applications where flexibility or movement is required, such as in areas prone to seismic activity. Modern concrete construction offers significant benefits, including versatility, strength, and cost-effectiveness, but it also faces numerous challenges that must be addressed for improved performance, sustainability, and longevity. Issues like cracking, corrosion, environmental impact, and durability in harsh environments are central to these challenges. To overcome these, ongoing research is focusing on developing alternative materials, improving construction techniques, and promoting better maintenance practices. Moreover, the future of concrete construction may involve integrating more sustainable practices and advanced technologies to mitigate these challenges, ensuring that concrete remains a reliable and enduring material for future generations.